All right, let's get started. Hi everyone, thanks for joining today's webinar, Scaling Optical Networks for the AI and Hyperscale Era. I'm Juan Pedro Tomás, editor at RCR Tech. Before we start, I have some quick housekeeping things. This webinar is being recorded and will be made available along with the slides after the event. You can submit any questions you may have for the speakers in the Q&A chat box throughout the conversation. After the presentation, we will have a Q&A session with our speakers. And also, please keep an eye out for the companion report coming out in the next few days. In this webinar, you will hear from industry experts about the technologies and strategies enabling next-generation optical and fiber networks to support the rapid growth of AI workload, hyperscale infrastructure, and data center connectivity. Joining me today are Jimmy Yu, Vice President at the Loro Group, Rob Shore, Head of Optical Network Solution Marketing at Nokia Network Infrastructure, Noah Taylor, Head of Market Intelligence and Growth Strategy Broadband at AFL, and Helen Xenos, Senior Director of Portfolio Marketing at Siena. Before handing it off to our speakers, I want to provide a really quick overview of the topic to be covered in this webinar. The rapid rise of AI workloads, large language models, and hyperscale cloud infrastructure is driving a new wave of demand for network capacity across data centers and digital infrastructure. As AI clusters grow in size and complexity, operators face increasing pressure to scale bandwidth, reduce latency, and improve efficiency, while also controlling cost and accelerating deployment timelines. Optical and fiber networks are emerging as critical enablers of this next phase of AI infrastructure. Advances in high-capacity fiber, coherent optics, integrated photonics, and network automation are helping operators meet growing performance requirements while supporting increasingly distributed and interconnected data center architectures. Now that we set an initial frame for the conversation, our speakers will dive deeper into this topic. All right, Jimmy, I'm going to hand it over to you now.
All right, great. Thank you. Thanks, Juan. All right, so as Juan mentioned, I am an analyst for Delaware Group, where I track the optical transport market, which is really the connections outside of the data center, so connecting data center to data center. Before I go into this slide, though, I did want to just frame the environment a bit on sort of the CapEx environment. So, there's really two large buckets of CapEx out there, or customers for optical equipment. The first being, of course, telecom operators, and the second being the large cloud providers, Hyperscale. If you look at the sort of CapEx environment we're in for telecom, it's been over the last, I'd say, 5 years, it's been actually fairly flat. I mean, we have some expansion, some contraction. We're probably more in the contraction phase, but it's been roughly flat for the last 5 years. If we look at the cloud providers, though, for the most part, it's been growing about 10 to 15% a year, the CapEx. And it wasn't until 2024. So when ChatGPT kind of came out, and I believe it was 2023, all of a sudden there was this flurry of activity, and we saw the CapEx from the cloud providers, especially the big hyperscale, jump up to about 50%. And it went up 50% in 2024, 50% in 2025, and we're expecting the same thing in 2026. But on the other hand, the telecom CapEx, we do expect that to decline in 2026 by about 2%. One other just metric that I think is important is capital intensity. So capital intensity is the CapEx divided by the revenue of that operator. And if we look at the capital intensity of telecom operators, we're going from sort of recently, it was 18%, and now we're about 15%. If we went back in time to, say, the 1999, 2000 build cycle, where we had to build the infrastructure in advance of really enjoying the benefits of, having websites and being able to interact over the internet, capital intensity was well above 30%. In fact, I don't actually have the figures, but I believe it was somewhere in that 30% to 40%. The reason why I point that out is if we look at the capital intensity now of the big cloud providers, it's somewhere in that range, 20% to 40%. And so we're sort of, in some ways, we're kind of reliving this. You got to build everything in advance. You got to build it in order to have the necessary infrastructure to consume and to enjoy the benefits. And of course, the benefits we're talking about now is AI. Okay, so with that context in mind, if you look at this chart here on the left here, this chart, what I'm kind of showing is when I look at the total spend for optical transport equipment, and this is just the hardware, no services. If you look at it over time, the money going towards optical transport, a lot of it was direct spend for data center interconnect. You can see the lines kind of been trending nicely, very linear. On a revenue dollar basis, it's been growing about 10% CAGR, very similar to the CapEx spend. Then sometime in 2025, it sort of accelerated, and the amount of DCI purchasing jumped by 40%, while the rest of the market was relatively flat. Very similar to my comments about the CapEx environment and who's spending money, where's the money coming from. So in 2025, we're at 33%. And just to put this in perspective, if we look at just North America, where a lot of the data center activity is occurring, that ratio would actually be closer to 60%. So about 60% of North America spending come for direct data center interconnect equipment purchases. Looking forward, you can see I still think that percentage ratio, we're on this accelerated path still in 2026. As I mentioned, the cloud providers are planning to increase their spend by 50% or so on average. The top four cloud providers, they're talking 70%. We're talking, $1 trillion of CapEx out there. I mean, optical is a small, very small percentage of that, but we are seeing this huge amount of CapEx spend, and we should see things kind of growing from there. What's also important to say here is if you kind of think of it another way and you look at this curve, and I know it's just a line, but if you kind of look at this sort of low, slow, linear growth, and then we see the step function up, and then I'm kind of expecting maybe we come back to more linear, normal growth. What I'm really also portraying here is that because of AI, the demand for optical has actually had a step function up, or the demand curve has actually shifted up because there's just new applications for the optical equipment in data center interconnect. Now, beyond direct, and just to remind you, this is just direct spending. There's actually indirect spending, and that's important to note because while the hyperscales and the cloud providers are buying equipment for their own use, they can't build everywhere. It's just impossible for some of these hyperscale to build in some parts of the world, whether it's India or China or anywhere. There's regulations, resource restrictions. There's just a lot of things that sort of get in the way. The hurdles are too big. So they look towards it. They turn towards communication service providers, CSPs, to say, hey, can you help me build a network to connect these data centers? It could be a leased wavelength. It could be a managed service, or the most popular right now is MOFIN, Managed Optical Fiber Network. We're seeing a lot of activity there. Also, sort of indirect and direct is we think there's going to be more enterprise or public spending on infrastructure, whether we could call it upgrade. But I think the reality is if they want to be ready for AI, they will have to invest in their infrastructure, whether it's directly by buying some equipment and interconnecting, their on-premise servers to an off-site storage site, or it could be through, of course, managed service with an operator, a CSP. So we do see that also. It's not in these numbers because it's really hard to track that, but I definitely feel that amount of spend, this indirect for DCI, is also growing as well. The last point to make on here is this sort of shift in demand. One of the reasons why we're also seeing the shift in demand is we're going beyond just the traditional data center interconnect, where we're just doing, say, YouTube videos and kind of, growing to match the capacity needs of more video content. We are seeing more of this sort of token traffic, and people talk about elephant flows. And of course, on top of that, the interest is in this new scale across data center interconnect concept where you're now connecting the back end of AI data centers. Okay, we go to the next slide. The equipment that we're seeing most favored for this DCI is what I call disaggregated WDM, but it's actually not a term I came up with. It was created a long time ago, I think back in 2013 or so. Uh, the interest was from the hyperscale is they wanted to have equipment that was sort of more purpose built for their needs, for the way they're used to deploying equipment. So at the time, we used to always kind of reference the way they bought these 1RU servers and they sort of racked and stacked and bought as needed. So the concept really grew out of there, and they also wanted open interfaces. They didn't want vendor lock-in. They want to be able to buy the best of breed technology at the time. So they wanted to really disaggregate the WDM down to its core building blocks. The first was transponder unit in a compact form factor. So as I mentioned, pizza box shaped. And then it was next we're seeing is optical line systems. So that connects the two transponder units, and it does all the muxing into a single fiber. It does amplification. And then more recently, since now we're able to disaggregate even further because technology has miniaturized the optics, we now have these ZR plus optics, and those are also something that can go onto a router and be bought separately. And I will also add, when the concept of disaggregated first came out, I kind of questioned it a bit. I kind of thought, hey, aren't we just going to all move to white box, or won't it just be that every vendor has the same box? But what I found out over time is what this is creating, or as an effect, is more rapid technology evolution. So if we take transponder units, for example, to do well in this market, you had to have the best transponder technology in the market, which meant you had to keep investing in new coherent DSPs, new photonic integrated circuits. And the benefit, because they're in this sort of compact form factor, they could get launched into the market quicker, they ramp in production faster, and the revenue stream back to the system vendor happens at a faster pace. And then, we move on to the next technology, and it kind of pushes forward. We're seeing the same thing now with optical line systems because we want more open interfaces, something that interacts well with third-party transponders, and of course the ZR optics. When you look at this chart, I'm showing 2022, 2025, and 2028 as my projection. In 2025, it's about $6 billion, a mix of the ZR optics, the optical line systems, and transponder units. If I were to add in the sort of the router chassis overhead, this would be closer to about 6.7 billion. Looking at 2028, amount of spend should about double, if not more. A lot of the growth I see is in the ZR plus optics. One of the reasons is a lot of the activity around connecting the back end of GPU data centers, so scale across DCI. And of course, optical line systems, because at the end of the day, you still need amplifiers and muxes, demuxes to connect the ZR optics and traditional transponder units. So that should more than double. If I were to layer in the routers and data center switch portion, that would add another 2 to 3 billion on top of that figure. Moving to the next slide, my sort of key takeaways. First is, of course, DCI demand is growing fast, 40% in 2025. I'm expecting another 40% in 2026. We're seeing a lot of the spend accelerating recently because of activity for AI. We're going not just a traditional DCI, where I think a lot of that was, we could kind of say it's connecting the front end of CPU servers. We're now going to connect the back end, the GPU servers. and we're calling that scale across. And of course, as I mentioned, enterprises are preparing for AI, and that means they will have to upgrade their network and connections into uh, or towards cloud provider data centers. For disaggregated WDM, I see a demand in all three of these technology subsegments growing. A lot of innovation in transponder units, a lot of innovation in ZR optics. I actually think the next phase is just more innovation in optical line systems. And, and that's, of course, because we've kind of reached Shannon's limit when it comes to spectrum. So what's the next phase? We got to deploy a lot of fiber and a lot of line systems. And I'll conclude there. Thank you.
Thank you very much for your presentation, Jimmy. Rob, please go ahead with your presentation.
Great. And thanks, Jimmy. And we're going to build on that a little bit. So you outlined kind of the growth and how the market's going to go moving forward. And I just want to dig into a couple of those statistics to give people a scope of the scale of what we're talking about. So on the next slide. And I'm actually using some of your data, Jimmy, from Deloro on the left-hand side. But the amount of spending associated with data centers, particularly in the AI supercycle, is really just absolutely astounding. Over the next 5 years, they're projecting about $5.5 trillion will be spent on data centers and AI infrastructure buildouts. That, by the way, would make it the third largest country in the world by GDP. So huge amount of spending. And what's that actually doing to the network? Well, on the right-hand side, you can see the inter-facility traffic is growing extremely rapidly at about 23% between locations. And equally, if not even more impressive, is what's happening inside the data center, where the traffic is growing at about 65% per year. So that's just really astronomical. As Jimmy mentioned, because of hitting the Shannon limit, you can only put a certain amount of information on a fiber. People are having to deploy more and more fibers to support these applications. So you can see about an incremental 1.2 billion kilometers of fiber are planned to be deployed in the next couple of years here. And then, of course, the optical interfaces themselves, even though the speeds of each of the interfaces are growing, on top of that, the volume of interfaces is growing just really, really massively. So coherent interfaces should triple, if not more. A lot of people think that numbers for 2030 should be more like 5 million coherent interfaces between locations. And then inside the data center, you're looking at a factor of 4 plus of incremental interfaces inside the data center. So just massive, massive spending and massive scale. Okay, so flip on to the next page. One of the things we're having to contend with, as we mentioned, is this concept of reaching the Shannon limit. That's the theoretical maximum amount of information you could put on a single fiber. So bandwidth continues to grow, but the capacity of fiber is not. So what that's doing is it's causing people to deploy connections with many, many more fibers. You're using a lot of fibers. In some cases, as you'll see on the next slide, as many as 8,000 fibers between locations. On top of that, I think everybody recognizes power is becoming an increasingly scarce and valuable commodity. So two of the big drivers here is how can I better leverage multiple fiber infrastructures, and how can I develop more power efficient solutions? And that's one of the biggest trends that we're seeing is this fundamental shift in innovation focus. So if you look at the two key things we innovate across in optical networks, the line systems and the engines, we're really transitioning from about 30 years where our focus was maximizing the amount of capacity per fiber. So really investing in these engines, these big, powerful engines that could really pack as much information onto the fiber as possible. And what we're transitioning to is less spectrally efficient solutions, but much more cost, space, and power optimized. So what you sacrifice a little bit of capacity per fiber, you're making up for in cost, space, and power. And part of the idea there is that network operators are no longer thinking about, I have a single fiber pair between locations. How do I maximize that investment? And instead thinking, I've got 7,000 fibers between locations. How do I minimize cost, space, and power? And so there's a big shift that we're seeing in innovation focus. So click next slide. So again, speaking about the number of fibers, we're going from an era where we were deploying maybe 200-ish fibers between locations to deploying, thousands. And in fact, I saw Zayo presented at OFC where they're putting as many as 13,000 fibers between locations. So one of the key things we need to innovate across to make these types of deployments more efficient, these massive multi-fiber deployments, is evolutions in the line system. So click. So the first thing we did is innovated on the terminal endpoints. We're going from the historical model on the left, where we had these very modular based solutions where you can mix and match different components to create all kinds of different configurations, to a much more simplified and high scalable implementation on the line systems with what we're calling these hyperscale OLSs, which use these direct attach ROADMs, and I don't need the drop structure, and you plug in the transponders directly into the line system, and it's just a single module does everything. So smaller, more power efficient, and perhaps most importantly, operationally simpler. Another click. Then we're moving this year. You'll see a bunch of announcements happen at OFC about what we're doing at these intermediate inline amplifier locations. These are little huts. They're like a double wide shipping container, so very, very space constrained. So we've been spending a lot of innovation effort on increasing the density of these inline amplifiers. And you'll see, and a number of people made announcements at OFC about this. But you're seeing this where you could put maybe 20 inline amplifiers to amplify 20 fiber pairs bidirectionally in a single rack, to solutions now that can do as many as 160 inline amplifiers. So still a one rack for 160 fibers. Obviously, we still have more innovation to go to get to 7,000 fibers. But this is, again, one of the key steps here. And of course, the focus on these inline amplifiers is reducing the space required, because these huts are very, very small. And space is the number one driving criteria there. So these are innovations along the line system. And I think you'll continue to see more power efficient, space efficient solutions as we go forward. Next slide. So now let's shift our focus to the engines, the optical engines. And this generation that we're in right now, we did see a pretty substantial evolution with the introduction of these coherent pluggables. This was really the first major step in these multi-hull, so multi-distance transceivers that are really focused on space costs and power optimization. And that's these 800 gig. And the demand for these is really shooting through the roof as a result, right? So multi-fiber deployments where I don't care so much about spectral efficiency, and I can really have an extremely space cost and power optimized solution. You still have some demand for the embedded solutions, which are more expensive, more power hungry, but they will get you more capacity per fiber. So if you're truly fiber constrained, there's still people that deploy those in quite good volumes. But really, the uptick on these multi-fiber infrastructures that are space cost and power optimized is really taking off. But this is today, and we really are solving pretty much all network applications today with these two solutions. So going forward, what do we need to do as these demands really start to skyrocket? Click, please. You're seeing this great divergence. Click one more time, of applications. So there's these really more specialized applications that each have different criteria, and the volumes for each of these applications are big enough that it warrants a unique, dedicated custom development for each one, right? And in addition to the applications, which are in those blue boxes, there's also an increasing number of deployment scenarios, different ways people want to deploy those technologies, whether they're based on these CPO switches or regular switches, routers, in a thin transponder, so pluggable in a transponder. In some cases, a single transponder that can fill up the entire fiber with one module. And then, of course, the traditional embedded transponders. And they want a mix and match of all of these things. So if you click one more time, I think what you're going to see going forward is, instead of like just a new generation, one more, please, another generation of a new pluggable and a new embedded engine, you're going to see a shift in the way we bring these solutions to market, right? That we're going to be moving more towards this kind of building block approach, where in those colored boxes, you'll have these optical engine building blocks that each are optimized for a different type of application. And then they can be seamlessly integrated into all of these different implementation methodologies. So if you look at, for example, like the IP over DWDM pluggables, so pluggables that go directly into routers, you could build those with two different types of building blocks, these really low power, short reach optimized versions, or higher power, but much longer reach optimized, or perhaps, super high power and higher performance. So this is the idea. The idea is to have more solutions that can be optimized for more applications. So it will no longer be a situation where here's one pluggable and one embedded, and now try to fit that into all of your applications. These hyperscale operators, they won't tolerate that anymore. And they're going to go and increasingly demand solutions that are really customized. And their volumes are big enough to justify that. So I think you're going to see, not I think, I know you're going to see in the future a much wider variety of optical engine configurations, both the building block and the implementation, to address these. And this is good for everybody, by the way, not just hyperscalers. This is going to give the entire industry more options to choose from. So when they have an application, they'll have the exact solution that fits that application without wasting any space, cost, power, or performance. Okay, so this is the inter facility. If we click again, let's take a really quick look inside the data center. So if you think the volumes of transceivers between data centers is big, they are nothing compared to the amount of units inside the data center. And you can just see between DCI, which is up at the top there, and scale across, those are kind of inter facility applications compared to the scale up and scale out. So connecting GPUs in a rack and connecting GPUs between racks. Huge numbers of interfaces. Click again. So as we're going to innovate for optical solutions inside the data center, it's really driven by these three primary drivers, right? Of course, increasing speeds. There's a bunch of electrical interfaces that need to go to optical because electrical has speed and distance limitations. And then, of course, number one driver inside the data center is power. Click again. So I'm now going to go through each one of these potential solutions in great detail. No, I'm just kidding. I'm going to really, there's so much to go through here. This could be an hour session all by itself, but there's a lot of different ways to solve these intra data center connectivity solutions. Today, they're mostly done by these PAM4 pluggables, direct detect, so relatively low power and modest performance. And there's a whole evolution path for those to reduce the power, primarily by removing the DSP, whether it's linear receive optics, linear pluggable optics, or these co-packaged optics or near packaged optics. Just a bunch of ways to implement them. And then there's a variety of other short reach alternatives too, like there's people talking about leveraging copper with radio frequencies or LEDs or VCSELs, things like that. And then some new standards coming out like coherent light and this new XPO MSA. So there's really a tremendous amount of innovation happening inside the data center, and it's all about increasing speeds while reducing the power. Okay, next. So really just in summary, right, massive, massive growth. There's all kinds of new applications and challenges, whether scale across or intra data center or increasing DCI or data center distribution. And it's really a really fertile ground for people looking to innovate new optical solutions. And there's going to be a pretty significant demand for that. And I think you're going to see a whole host of new solutions coming out in the coming years. So Juan Pedro, that is it for me. I can hand it off
Great.
to them.
Thank you very much, Rob. Noah, I'm going to hand it over to you now.
Thanks, Juan Pedro. Good morning, everyone. Great to be with you all. My name's Noah Taylor, and I work for AFL. We are a global manufacturer of fiber optic products as well as connectivity, and we also are involved in the conductor hardware accessories as well. So really touching all sides of AI from both an optical standpoint as well as a power standpoint. If you're not familiar with AFL, we were founded in 1984. We're primarily in the North American market, about 85% in NA, but we do have a presence in EMEA and APAC region as well. Both are products and a services company, so we understand both sides of the build, and over 12,000 worldwide team members in total. Next slide, please. So I want to start and set the table with a couple slides here about where we are, where we're headed, and then we'll dive into some specifics around the physical infrastructure, the layer one infrastructure for AI. Computational demand has skyrocketed. And to put that in perspective, ChatGPT reached 100 million users in 60 days in November of 2022. And today we see AI agents at over 100 to 1,000 times compute of what they were before. And this is, again, in January 2026. We continue to see this scale. And what this boils down to is not only the compute, but also the bandwidth requirements that we're starting to see in data center AI scaled networks. Next slide, please. when we think about from a business growth standpoint, a lot of focus and attention is on the data center growth. But what a lot of people don't realize is that DCI is actually scaling as much or more than what we see in the data center market. And the reason for that is quite simple. If you look at that graphic there on the right, data center interconnect, once you interconnect more than 3 data centers, you start to have more interconnects than you do data centers. And this is just due to the nature of trying to interconnect each node in the network. And so because of that, not only are we seeing tremendous growth from a compute standpoint to interconnect all these data centers as we begin to talk about scale across, continue to be a theme and something that we're going to see a lot of pressure on. Next slide, please. And so, again, this impacts the topology of how you arrange the physical elements of the network. What used to be maybe a star or ring design with some redundancy, now we're starting to see a push from our hyperscale customers for a mesh network design. And so this includes, in some cases, 3 to 4 data center interconnects for a single data center. So not only are we seeing computational demand spike, we're seeing more data center interconnects than data centers. We also want redundancy built into our networks. And so we're seeing a huge push for a mesh dynamic and scalable network topology. This continues to scale as we think about scaling the optical network. The second part of that is also thinking about how this influences the entire ecosystem, including the access network. And so both Rob and Jimmy did a great job of kind of defining both DCI and 2 aspects, but just for a light review, in this example here, we're showing intra DCI as connecting data centers on a campus, but then you have the long haul or ultra long haul DCI that's connecting campuses, say from Atlanta, Georgia to Virginia. We're seeing a lot of pressure and an investment today in the long haul networks, and a lot of density technology is being deployed in data center interconnect. But we're also starting to see some pressure as we scale AI and we continue to build out the scale across. There's a fundamental squeeze and a traffic clip that we're seeing from an access optical network technology standpoint. And so if you think about traditional cloud loads, we used to download videos, watch things on our personal PC that we would download from a cloud. But today that paradigm is starting to shift. It's no longer just traffic from a download standpoint. Now we're starting to see a tremendous uplift in the upload. And again, this goes back to moving from that AI agent inference model. We're starting to pass a lot of information up towards these models for inferencing purposes. So this includes pictures, videos, sensing data that you may have out in your network. A lot of this is also going to start to put a squeeze on our metro and middle mile networks as well. Next slide, please. So this brings me to kind of the central takeaway I have for you this morning is the interconnect tech stack, or 3 key things you have to have if you're going to interconnect your data centers effectively. One of the first things and kind of the bedrock, the foundation, if you will, for scaling AI is density. You have to have a massive amount of high density networks to avoid any type of costly overbuild, and quite frankly, just to scale AI as we're seeing the growth today. The second aspect of that is speed, and this is really the catalyst is what I call it. And I'm not talking about just bandwidth and latency speed, but really the speed of deployment. So how fast can you splice, install, and are you giving your installers flexibility, both from a conduit standpoint as well as a placement standpoint? And then the last part of the interconnect tech stack is the ecosystem, the enabler. Density is really table stakes at this point, and I think speed of deployment is increasingly becoming important. Any amount of lag that you have to have a server sit idle is really a massive loss in potential revenue. And so the ecosystem really kind of pulls all this together and helps both the density and speed standpoint from a hardware standpoint. You have to have an ecosystem of products that help support both the density and the speed. So this interconnect tech stack is really 3 key things that you have to deploy DCI effectively. And next, I want to touch each one of these just a little bit deeper, starting with density. So when you think about extreme density, and I'm talking about anywhere between 6,000 to 13,000 plus fibers in a singular cable, there's really 2 things you need to look at. One is the fiber technology. And if you're looking for a great fiber technology, look no further than AFL spiderweb ribbon. This is a unique compared to a standard matrix ribbon, which may be glued all the way across all 12 fibers. With an intermittently bonded or spiderweb-like ribbon, you get that spiderweb look because we're gluing individual fibers there to produce that spiderweb look. It's an intermittent bond, and what that allows you to do is really collapse that ribbon down and bunch it into a very tight space, which leads to point number 2, which is cable technology. At this point, as I mentioned, I think density is pretty table stakes for high-density cables in the AI network. But what a lot of people overlook is the cable technology itself, right? There's a lot of things and innovation that we're starting to put into these cables to help with the speed of the deployment. And I'll give you one example from a cable standpoint. AFL is now designing our air-blown wrap-in-tube cable with a corrugated outer jacket, and that really assists the speed of deployment for the installers. On top of that, as we move into the second pillar here for speed of deployment, I think there's a lot of things I could bring up, but what a lot of people don't think about is the fiber that's being deployed. Today, a lot of hyperscale networks are deploying 200 micron ribbon fiber, but the issue and the things that we're starting to hear from our customers is they're having issues with 200 micron ribbon interfacing with standard 250 micron ribbon that's out in the field. And I think the example is pretty clear there in the graphic below, but conventional 200 micron ribbon just simply does not align in the V grooves of the splicer for 250 micron. And when you think about how this scales for over 6,000 to 13,000 fibers, this can be quite a headache for a splicer and slow them down considerably. Then when you span that into a long haul network with multiple splice points throughout the network, this is a real issue and can slow down the deployment. And so one of the things we've done with our 200 micron ribbon is we've adjusted the pitch of the fiber to equal 250 micron. And so as you'll see on that graphic there on the left, it allows the 200 micron ribbon to perfectly align with the existing 250 micron ribbon that's already out and deployed into the network. So this is just one example. There are several of ways you can speed up the deployment. And again, that's about getting that data center up a lot faster, give your hyperscaler a better speed to revenue so they can get those servers turned on quickly. And then the third point, as we transition into the ecosystem, really the top of the stack here. And if you'll go ahead and change the slide. The ecosystem is really about building on that foundation of density. And density can influence the ecosystem in several ways. I'm listing four here. One is the influence it will have on conduit and the future impacts of trying to overbuild cables in the future. If you have a really high density cable, that can affect the type of conduit that you're going to deploy and really give you the ability to have multiple open future pathways that you can install cable in the future. And that goes back to what cable technology you're leveraging and how high is the density of that cable. And then number two is the storage and the closures. You want to look at a closure that's designed to work and leverage with high density cable. And so here I'm thinking about our Apex splice closure. It was designed with spiderweb ribbon in mind. And it's a fantastic closure that helps leverage that density aspect that we see now required as we scale across. And the number three is a splicer. We talked about the ribbon already, but you need an intelligent ribbon splicer that's designed to handle those complex workloads. AFL just released our 100R splicer, and it's a perfect case in point for an intelligent ribbon splicer that was designed to work with these high AI workloads for those 6,000 to 13,000 fibers that need to be spliced as quickly as possible. It's built with a couple tricks up its sleeve to help on the speed side of things. And the last way, logistics. I think this becomes increasingly important as we think about the conflict in the Middle East. If you have a high density cable, you can fit more on a reel, which allows you to fit more on a truckload and save from a freight standpoint. I think another example of this would be handholds. AFL Switchblade handhold is a collapsible handhold, which allows you to fit more on a truck, save more on the logistics side. And again, it's not just freight. It's not just shipping it from the manufacturer to the end user, but it's also intracompany transfer, right? As you move this to locations on your project and even lay down yard space, this impact on the ecosystem is very clear. So there's a lot of things you need to think about from both a density and a speed standpoint, but then the ecosystem of how all these products come together for that DCI deployment as we scale across is critically important. And now as we look forward, once you get the interconnect tech stack, we're starting to look forward into how do we affect each three pieces of these components, both the ecosystem, how do we continue to increase the speed of deployment, but also leverage density. And a couple things I want to call out here is from a new fiber technology standpoint. There's two new technologies that are really starting to push the physics with both hollow core and multi-core fiber. So with single mode fiber, you have a solid glass core is where you transmit the light. Typical attenuation or loss is around 0.2 dBs per kilometer, and your propagation speed is really limited by the refractive index. With hollow core fiber, it really solves both a latency and a loss problem. Hollow core fiber is transmitting the light in an air core, and so that's going to be 50% faster than standard single mode fiber. When you think about how that scales over long distances, hollow core is a great example of saving from a latency standpoint. And then also from a loss, we're seeing really low, ultra low loss in hollow core fiber around 0.09 dB in some trials that we're starting to see. So great technology and something we're going to see help leverage both a speed standpoint and a density standpoint. And then if we look at multi-core fiber, this is taking that standard single mode core that you have with single mode fiber and multiplying that by 4. And so I think the graphic there shows it greatly. If you take a 144, what used to be 12 bundles of fiber, now you can reduce that to 3 if you have a 4-core multi-core fiber. So when you think about the density vector of innovation, multi-core fiber is right along with that. I think we push the limits on single mode fiber, and multi-core fiber will be the next natural evolution of that technology. Next slide here, and kind of wrapping up with some challenges. So as we think about these new fiber technologies, they're not without their challenges. And 4 I want to bring up real quickly. One is standardization. I think from a hollow core standpoint, there's a lot of different cores out on the market today, and we continue to see standardization efforts for hollow core, trying to bring some standardization to that core design. We've seen a lot of progress in multi-core fiber. So just this quarter, AFL and several other manufacturers have come together on some standardization efforts for both multi-core fiber and its connector ecosystem. And then multi-core fiber interfaces. Unless you have multi-core fiber links end to end, you're going to have some type of transition. And I think we've yet to see a strong growth in how we're going to address that as a marketplace. So that's going to be a challenge we'll have to overcome as we look into the future. And then the cost of polycore fiber. It's quite high today, but I think as we continue to find use cases for it and scale the production there, we should see that cost to make it more deployable and have an ability to utilize that technology to lower the latency envelope. And then lastly, the handling for hollow core fiber. A much higher bend radius is current in the current designs of hollow core fiber. And so if you have a technician who's used to working with single mode, this is going to be a challenge, right? As we get out into the field deployment side of hollow core. And so that's something we're going to have to handle as well, as how do we design the cable from both a density and speed of deployment so that the technicians can deploy this effectively at the correct speed for data center interconnect. So as I wrap up here, kind of in summary, is really thinking about that interconnect tech stack. The 3 key things that you need for interconnect is the density. You have to have that. It's really table stakes. And then speed of deployment. You can have all the density of the world, but you have to be able to deploy that at scale quickly. And then lastly, do you have a supporting ecosystem that supports that interconnect tech stack? And with that, Juan Pedro, I'll hand it back to you.
Great. Thank you very much, Noah. Helen, please go ahead with your presentation.
Welcome, everyone. We can move to the next slide, Hannah. Okay, so I'll start by just taking a step back and let's look at what data center interconnect is. And you can see it's a lot of different use cases. Traditionally, we think DCI, we think of the front end network, 2 data centers interconnected within 100 kilometers. But we're also interconnecting data centers across the country with the backbone network, across between continents with our submarine networks. There's shorter distance, like campus applications, and then you scale across applications that folks have been talking about in this webinar. You can see where it fits in here. It's really part of the backend network where we're extending the scale out part of the network to a second facility. And the distance between those 2 sites is going to depend where we can find power and real estate. Big difference with the scale across is massive capacity, 10 times more capacity than what we would see in Metro DCI. And also it's lossless connectivity. So very reliable connectivity is also needed there. Next slide. But even for each of these specific use cases, it's not a single technology that is being deployed. So it really depends on what is the biggest constraints customers are facing, or what is their top requirement. Is it power efficiency is most important? Is it getting the most capacity in the smallest space? Is it you need 400 gig or 800 gig connectivity across any link in the network? Is fiber scarce? Is it very expensive to secure? Or are you leasing fiber? Then spectral efficiency is your top priority. Or is it deployment velocity and operational simplicity is the most important thing? And if you go to the next slide, Hannah, you can see that depending on what the answer is to that question, that will drive the technology or architecture choice. And in particular, there are some new architectures here at play that I'm going to be speaking about. Next slide. So Metro DCI, this is, I'm showing you two examples here. Industry-leading technology from both a pluggable and a performance transponder perspective, and 800 gig, you can achieve 51.2 terabits per second. With WaveLogic 6E, you can achieve 76.8. What is the right technology to use here? Well, it depends. Do you care more about power and space optimization? It's coherent pluggables, and that is the most popular choice. But we are at the same time seeing neoscalers that are building their new networks, their optical networks for the first time, and have very limited fiber assets and are using WaveLogic 6E because of the extra capacity that is deployed there. And as we move forward, we are evolving and building next technology for both pluggables and transponders. The rise of scale-across networking we've been talking about is here, actually. We are already shipping in volume systems to satisfy scale-across deployments. And the specific capacity and reliability aspects of scale-across networks have driven simultaneous innovation in both the coherent optics as well as photonic line systems. From a photonic line systems, we needed now C+ L-band for point-to-point passive configurations, protection switching, very simple to operate systems. From a coherent pluggable perspective, we wanted the latest, next generation, most capacity, interoperable with interoperable 800 gig CR+ with interoperable PCS, and the fact that we have both C and L band variants allows us to double the fiber capacity there. So this is a great solution when the scale across network is within a single span. But what happens when you need to go beyond 150 kilometers? And now we're talking about multi-span networks. If you go to the next slide. Well, if you use existing photonic line system design today, amplifier huts have been designed to support, let's say, 16 fiber pairs per hut, and you can support all the capacity within a single hut. When we're talking about this new scale across or AI infrastructure scale, 20 petabits per second as an example, if we're using conventional line system designs, we would need 22 huts to actually support this capacity. And this is a single example here. You can see this is not a viable solution, very expensive to secure all and build all of these huts. Next slide. This has driven dramatic innovation from a photonic line system perspective and multi-rail photonic architecture. With Sienna RLS hyperrail solution, here I'm showing an example, we are able to achieve 32 times density improvement over today's present solutions and be able to fit all this capacity in a single hut. So incredible innovation here. Multi-rail, sorry, couldn't go back. Multi-rail photonic architectures are enabling this AI scale capacity with a fraction of the infrastructure. And why did we select 128 rails per rack? Because this allows for maximum capacity, but the ability to also satisfy existing hyperscaler powering as well as operational requirements. Next slide. Okay, what about deployment velocity? If that's the most important thing for you, you want to deploy quickly. Today, optical networks, we're deploying single wavelength at a time. And so if you're deploying, let's say, filling up a fiber with 800 gig plugs, it's 64 plugs on one side and 64 on the other location. If you're turning up tens or hundreds of fibers, you can see this is becoming increasingly operational complex. This is where full spectrum transponders come in. that allow you to light up an entire fiber at once. And you can see an example of what this looks like here. We're connecting client interfaces into a full spectrum transponder. The coherent optics, wavelengths are all inside, going into a channel mux demux, and then coming out of a single line port where you have the full CNL band capacity in the single line port that you can plug in directly. You can see how quickly that allows or that enables cookie cutter deployments. Next slide. So how are optical networks evolving? And I can walk you through this phased approach here. The present mode of operation is at the top where we have, let's say, 32 transceivers going to a ROADM line amplifier module. This is happening at the terminal, going along the network where you have individual lineup modules, each for a single fiber pair. As a next step, we replace those 4 lineup modules with a single hyperrail module. And now, the next step after that, well, if we're turning up tens or hundreds of fibers at a time, we don't really need the ROADM here. We can simply replace that with the same hyperrail module. And now all that's left is channel mux demux and the transceivers, which, again, now you're replacing with a full spectrum transponder, as I showed you earlier. So you can see how this is evolving. Optical network architectures for AI are evolving to these simpler architectures that are, these repeatable cookie cutter type of deployments. Next slide. So one more constraint that's coming ahead of us and that's impacting architectures, new limits of optical scaling are density and power. So routers switch ASICs are scaling from 50 to 100 to 200 terabits per second, but the faceplate density is still limited to 32 OSFPs per open rack unit or per rack unit. We're being asked to put more and more capacity into these pluggables, but we're reaching air cooling limits. The industry is moving along 2 parallel paths to solve this problem as we move forward. The first is using co-packaged optics, bringing IMDD optics very close next to the switching ASIC, and then connecting separately. You would connect separately to a coherent device. Or to use liquid cooling, which allows more capacity in a pluggable, maintains the benefits of a pluggable, but now you require liquid cooling infrastructure. Ciena is developing products in both of those areas. And finally, to conclude, I think this kind of summarizes everything that I talked about. Different constraints are driving different optical architectures. Power efficiency, certainly coherent pluggables are very popular, will continue to be deployed and increasingly be deployed in more applications. Performance transponders for spectral efficiency. Full fiber systems we're building to satisfy deployment velocity as the key requirement. And thermal and density limit constraints are leading us to co-packaged optics and liquid cooling approaches. And there, as optical networks evolve for AI, we are going to see the coexistence of many architectures, not just one. Okay, thank you, Juan Pedro. That's it for me.
Thank you very much for your presentation, Helen. Now we will start with the Q&A session, and I have an initial question for you, Helen, which is how far can optical innovation continue scaling capacity, before the industry must rely more heavily on architectural shift such as multi-fiber and scale across designs?
Okay, as I talked about in my session, there's a lot of innovation happening in parallel across many vectors. So today in the industry, we're working to get higher baud coherent designs, both from a pluggable as well as a performance optimized transponder type of solutions. We're also looking at liquid cooling approaches like I talked about. and looking at different types of designs like full fiber system design. So, but at the same time, looking at new fibers like hollow core fiber. So there's a lot of innovation happening in all aspects across photonic line systems, coherent technology, et cetera.
Great. Thank you very much, Helen. Noah, how are AI workloads changing requirements for fiber density, cabling design, and physical infrastructure inside hyperscale and AI data centers?
Thanks, Juan Pedro. Great question. I think I'm hit on this a little bit, but we're just seeing a huge surge in density. We hit on this in several parts of the presentation, but we're reaching physical limits, I think, from a spectrum efficiency standpoint, where we're going to have to deploy more fibers. And so, how you do that, again, kind of in that interconnect tech stack, you need high density, but you also need speed of how you deploy that. And so, we're seeing a huge push for both the long haul side of the networks. And I think we're going to continue to see that trickle down as we get closer to the end user and the access network.
Great. Thank you very much, Noah. Rob, from your perspective, how are networks architectures evolving to support large-scale AI deployments, particularly in data center interconnect and scale across environments?
Yeah, I mean, that's the whole point of scale across, right? As data center operators are looking to increase the number of GPUs associated with a particular individual training instance, they just can't fit all of those resources in a single physical location. So we're seeing this really right now on very large scale, this massive distribution of data centers as operators are looking to build data centers where they can find power and then connecting them through the back end. So it's essentially a scale out application, but just across different physical locations, creating single larger training environments, training clusters, and that's how they're getting to this, million plus GPUs per cluster. And so that's one way is right this massive distribution in the training and for training resources. But I think you'll also see increasing distribution for inferencing as we take those learning models and apply them to real world applications. We're going to want to bring some of those compute resources even closer to the edge of the network. And so I think you'll see even more distribution and a wider variety of deployment scenarios, whether they're central offices or in mobile base stations or you name it. You're going to see compute resources everywhere and people looking to access them for a variety of different application needs.
Great. Thank you, Rob. Jimmy, which segments of the optical networking market are expected to see the strongest growth, let's say over the next 3 to 5 years as AI infrastructure scales?
Yeah, I think the easy answer is all the segments, but
Okay.
maybe the highest growth segments, I think to what Helen pointed out and Rob is a lot of the ZR plus optics. So we do expect to see a lot of scale across deployments with the just huge amount of fiber count, huge amount of ZR plus at 800 gig, driving a lot of the demand. And of course, as mentioned, with all that fiber, a lot of new fiber, you're going to need some type of line system. Of course, at the two ends, but then as the reach goes further out, eventually, inline amps will be a big investment. So I expect to see lots of sort of IP over DWDM ZR plus, lots of OLS being the higher growth rates, but growth overall.
Great, Jimmy. I have a second question for Helen. Helen, to what extent can current optical technologies delay or reduce the need for new fiber deployments, and where are their limits?
Okay, so with newer technologies, certainly we can get maybe 30 to 50% more capacity per fiber. So that certainly helps. But as we're seeing, we're showing capacity increasing by 10 times or more. So that is requiring, more fibers being deployed, new ways of looking at the problem and how can we solve the problem. So again, like I mentioned before, we are all investing in all these different vectors of innovation to enable more efficient deployments for our customers, the ability to turn up capacity very quickly for them, large amounts of capacity very quickly.
Great, Helen. Thank you. Noah, how is AI-driven demand changing traffic patterns and network requirements compared to traditional cloud workloads?
Yeah, great question, Juan Pedro. I think what we're seeing is a huge shift in just the traffic flow. really a reversal, if you will. What used to be download heavy, we're starting to see an upload shift. I think I mentioned that in the presentation a little bit, but again, this is kind of permeating throughout our networks, both from a fixed broadband. You think about fixed wireless as well as standard mobile broadband. I think all operators across the spectrum are starting to think about how do we make our upload and download more symmetrical. And again, it just goes into as we shift to the inference side of AI, we're going to continue to upload more and more from a picture, video, audio recordings, those types of media. It's going to go back into those inferencing models. And so I think we're going to continue to see this push to have more upload speed. And it's really going to get to a symmetrical standpoint, if not a flip.
Great, Noah. Thank you very much. Rob, what role will automation and software-driven operation play in managing increasingly complex AI traffic flows?
Yeah, it's a really great point. Obviously, we've been looking to automate networks for many, many years, but I think there's going to need to be some fundamental changes if you want networks to be compatible with AI workloads and AI applications. As I said, we're going to see more and more distributed compute resources throughout the network, and increasingly, you're going to have connectivity networks that are going to need to interface with AI workload orchestrators. And they're going to be looking to access these different compute resources throughout the network, and they're going to need a seamless way to interact with the connectivity network so they can make those requests, establish the connections, make sure they know where the bandwidth is, where the compute resources are. So I think it's more even now than just automating the transport or connectivity infrastructure for simplified operations. It's going to need to interface with some exterior workload orchestrator to enable those connections to be established to the appropriate workload. So it's never been more important than it is now, and some of those automation challenges are increasing and broadening their scope that need to be addressed.
Great, Rob. Finally, Jimmy, how much of the current optical transport demand surge is being driven specifically by AI-related data center interconnect versus traditional telecom or cloud infrastructure upgrades?
Yeah, it's actually probably a difficult question to answer directly, but kind of like the chart where I showed the demand curve sort of shifting up. If we were just to assume that without AI, that DCI spend would just continue to be linear, uh, you know, if that's the case, then I think about 20 to 25% of what being bought now in 2026 will be related to AI data centers and that sort of build. But just to note, I don't think AI traffic like token traffic's really that large at this point. So we're very early in the stage. You really have to build the infrastructure before you can actually use it. And that's important takeaway for me is just it's going to take a few years to build the AI infrastructure.
Great, Jimmy. Thank you very much. We have a few additional questions from the audience, and we will make sure we send those questions to our speakers. Now we are running out of time, so I want to thank everyone for joining, and a special thank you to our speakers. Thank you again, and enjoy the rest of your day.
Thanks, everybody.
Thank you.